Welcome. This project predicts the net hourly electrical energy output of a combined cycle power plant. The model uses 4 environmental measurements collected by plant sensors. Because the output is a numeric value measured in megawatts, this is a supervised regression problem. The solution was developed in Python and evaluated using RMSE, ME, and R-squared. The exercise is evaluated in 4 areas. First, the modeling approach must correctly identify the task, target, features, and possible algorithms. Second, model building must compare at least 2 alternatives using validation. Third, the selected model must be evaluated on a separate test set using a reasonable metric. Finally, the model results must be interpreted clearly in practical language. A key rule is that the test set remains untouched during model selection. The dataset contains 9,568 hourly observations. The 4 input variables are temperature, exhaust vacuum, ambient pressure, and relative humidity. The target, PE, is the net electrical energy output in megawatts. Initial checks confirmed numeric variables and no missing value issue. The target ranges from roughly 420 to 496 megawatts. Exploratory analysis also shows that temperature has a strong negative relationship with power output. For modeling, I used temperature, ambient pressure, relative humidity, and exhaust vacuum as the predictor features, and PE as the target. All 4 predictors were retained because each may contain useful operational information. Linear regression provides a simple and explainable baseline. Random forest and gradient boosting were also tested because tree-based methods can capture nonlinear relationships and interactions. Correlation was used for exploration only and was not treated as proof of causation. The data was split before any model comparison. 80% was reserved for training and model selection, while 20% was held out as the final test set. On the training portion, I used 5-fold cross-validation. In each round, 4 folds trained the model and 1 fold validated it. The average validation score was then calculated. This approach gives a more reliable comparison than using only one validation split and protects the final test set from influencing model selection. 3 algorithms were compared under the same 5-fold validation process. Linear regression served as the baseline and assumes a mostly linear relationship. Random forest averages predictions from many decision trees and can capture nonlinear interactions. Gradient boosting builds trees sequentially, with each new tree correcting earlier errors. The primary selection metric was average validation RMSE. The model with the lowest value was selected because lower error indicates better predictions. The validation results selected gradient boosting as the best model. Its average validation RMSE was 2.634 megawatts. The validation ME was 2.102 megawatts, and the validation R-squared was 0.9633. These results were better than the competing models in the notebook. Importantly, the winner was chosen from cross-validation results before examining the final test performance. After selection, the gradient boosting model was retrained using the complete training set and evaluated once on the untouched test set. The final test RMSE was 2.654 megawatts. The test ME was 2.115 megawatts, and test R-squared was 0.9626. RMSE was the main metric because it is expressed in megawatts and gives additional weight to larger errors. In plain language, the ME means predictions differed from actual output by about 2.12 megawatts on average. This chart compares actual and predicted output for every test observation. The diagonal reference line represents a perfect prediction. Most points lie close to that line, indicating that predicted values generally match the actual output well. The R-squared value of 0.9626 means that the model explains about 96.3% of the variation in test set power output. R-squared should not be described as 96% accuracy. Residuals are the actual values minus the predicted values. Here, the residuals are generally centered around 0, with no strong systematic tendency to overpredict or underpredict across most of the range. This supports the conclusion that the model fits the test data reasonably well. Feature importance can also show which variables contributed most to prediction, but importance is not causation. The model is most reliable within the environmental ranges represented in this dataset and may not generalize to another plant without validation. To summarize the 4 grading requirements, the problem was correctly defined as supervised regression, using PE as the target and 4 environmental features. 3 algorithms were compared using 5-fold cross-validation after holding out a 20% test set. Gradient boosting was selected using the lowest validation RMSE and then evaluated on unseen test data. Finally, RMSE and ME were interpreted in megawatts, R-squared was explained as variation captured, and residuals and limitations were discussed. This completes the full modeling and evaluation workflow.